Okay, awesome. Well, I appreciate it and always have a good time talking with this group. I came by animal science via reprophysiology from a really young age. I grew up with an ABS rep. So even though I'm a geneticist, always feel very much at home talking with my repro colleagues from across the industry. So Pedro asked me to talk about a topic that I get a ton of questions about, that being commercial genomic testing. I think we've seen a number of products come on the market in recent years. The price point has gotten a lot more attractive for commercial producers. And so I think that I like to give a little bit of context about what commercial genomics do, what they don't do, and other places where genomics should be playing into every single commercial herd. So with that, I want to start off with a really quick genomic test definition, I guess. So when I talk about genomic tests or genomics or commercial genomic testing, I want to be really clear that I'm talking about assays that capture the complete set of genetic material of an individual. So that's kind of a stuffy, sciencey sounding definition, but I think that what I mean by that is I really want to exclude the single gene tests. These were probably some of our first exposure to commercial genomic testing. We had the GeneStar tests for marbling and quality grades, right? And so, or for quality grades and tenderness. And so these single gene tests for complex traits or traits like coat color that we have known genetic markers for and we do genetic tests on, these are not the same thing that we're talking about when we talk about genomic tests or commercial genomic tests or genomically enhanced EPDs, right? These are single marker tests, typically for either, in the case of marbling and tenderness, large effect mutations in the genome that we're trying to capture, or for some of these more simple genomic or simple genetic either abnormalities or things like coat color, where a single marker can explain all of the variation that we see in that phenotype. But what I do mean by genomic tests is that we're assaying the entirety of the cow's genome, right? So there are about 3 billion base pairs, A's, C's, T's, and G's, as we look all the way across the cattle genome. And what we find is that if we squish the two genomes from two animals from the same breed together, we'd be likely to see about 1 million or 2 million differences in the nucleotides or the DNA of those individual animals. So that's what I mean by the genome. And what I typically mean by genomic tests are these assays that we've designed. They don't have all million differences or 30 million differences that might exist in, say, the Angus breed, but they do have enough markers to account for all the distinct chunks of the cow genome. So somewhere between 20,000 or 100,000 markers. Due to the way that DNA gets inherited, which we'll talk about in a little bit, we can use a small subset of intentionally chosen markers to represent that 3 billion base pairs of the genome, right? So that is ultimately what made genomics much more tractable for us, is the design of these high density genotyping arrays. So again, that's just a quick definition, but I want to spend most of my time talking about the nuts and bolts of what these things do. And then the latter half will talk about their direct applications to commercial herds. And so I think before we jump into heifer testing, which is probably what Pedro wanted me to talk mostly about, I want to talk about the one place that every single commercial herd should already be using genomics, regardless of if you've got 10 animals or 1,000 animals. The one place that every single commercial breeder should be using genomics is in doing sire selection. Our seed stock folks that are on the call will be much more familiar with genomic testing and genomically enhanced DPDs because we've been at it for much longer, right? We introduced these assays back in 2009 or so. Genomically enhanced EPDs come in online in the early 2010s. And so the seed stock industry has been genomically testing for a while, and it's nearly ubiquitous at this point. But I really want to underline, and I don't want to skip over the importance of genomic testing to our seed stock operations as a service to their commercial producers that are our customers, because of what these genomic tests do for enhancing our confidence in animals' EPDs. And so I always like to frame this bull purchase as one that carries a lot of risk. I talk a lot in economic terms when we talk about genetics, but when we think about a risky decision in an economic sense, a bull buying decision or a sire selection decision if you're utilizing artificial insemination, this is absolutely one of the biggest, riskiest things a commercial operation does. They're putting all their eggs in one basket if they're a small herd, or multiple calf crops worth of eggs in a basket, and making a decision on this single animal, making a big upfront purchase, whether that's buying a bull or whether that's going through an artificial insemination protocol, buying semen, right? There's all these moving pieces that make this a costly investment, but also one that can generate a bunch of income down the line, right? Or save on cow costs or whatever, right? These bulls are what drive commercial genetics forward, making sure that we bring the right bulls in. And so this is a risky decision. It's not a straightforward decision. There's lots of different moving pieces that can complicate this. But what EPDs do and what genomics in particular do is they help us mitigate the risk of getting this wrong, right? A wrong bull decision can end up with a bunch of calving difficulties if we select a bull that we think is a calving sire, but he's not. We can mitigate risk that daughters that we retain aren't going to stack up from a longevity standpoint. So again, I think about genomics and EPDs as risk mitigation opportunities. I'm going to skip through that because I want to spend more time talking about why we utilize genomics in addition to the EPDs that we've conventionally used in our bull selection decision. So the way that we increase accuracy of EPDs, and we'll reiterate this in a second, is to add progeny to the calculations within a particular breed, right? So bulls start off with some sort of an average of their parents' EPDs typically. So as we try and integrate more information into genetic evaluations, those young sires eventually will have progeny. Those progeny are from registered herds. That data gets recorded. We get more and more confident that that EPD represents the animal's actual genetics they can pass down to offspring. The issue with this, of course, is that young sires don't have any offspring in a genetic evaluation. A lot of our commercial producers who are going out and buying a herd bull, they're buying a bull that will never have progeny's records reported back to the genetic evaluation where his EPDs are calculated. And so, again, what we're trying to do in a sense in animal breeding is refine this really challenging problem of bull selection, right? So in a large population, these animals are highly related. The average bull is much more related to another animal within his breed than the 172 of us on this webinar are to each other. And these animals, of course, are raised across environments and management, but we're interested in identifying animals that have the greatest amount of genetic potential, the earliest in life. And I think that this is a repro crowd, so you understand the importance of generation interval. We want to identify that this bull is the best, regardless of where he was raised, right? He might be out in the middle of Montana, a long ways from Tennessee, but I want to know that he's the very best. And I want to know that at a young age so that I can have a jump start from a generation interval standpoint of getting those genetics into my herd. And our ultimate goal, of course, is if we identify these animals that are the best, and if we do it as early in their lives as possible, that's how we accelerate the genetic gain within our population. That's how we improve our herd. And in commercial herds, this is almost exclusively driven by the bulls that we bring in. Again, whether artificial insemination sires or whether herd bulls, the vast majority, 90+% of the genetic gain that we generate in our herd is going to come from getting this bull selection decision right, rather than from necessarily picking the correct replacement female. So again, this bull decision is very important, and I know I sound like a broken record, but this is where all of our genetic gain in commercial herds comes from. And so I believe this is my only equation of the night, but it's an important one in the context of genomics. So please do bear with me. The breeder's equation, we animal breeders and geneticists are addicted to, because this is really the foundation for all that we're doing, right? We're trying to make as much genetic gain, or this delta, that's the change in genetics on a per year basis. And that's a function of four main things. The first, and we'll come back to this because this is where genomics is really important, is our accuracy of selection. So, how correlated or how related is the metric that we're using to select our animals on? How well is that predictive of the actual genetics that a bull can pass down to its offspring? And so this is really, really important because there's some sort of a correlation between the visual appearance of an animal and the genetic potential for weaning weight, right? A bigger bull is likely going to have some genetics that contribute to early life weight gain, but it's not nearly as good of a predictor as an EPD, which we'll talk about EPDs in a second as well, which focuses just on the genetic component of that trait. So the ability to increase the accuracy of selection, how well does that selection metric represent actual genetic merit? That's a very, very important piece to driving genetic progress. And then the other pieces, we'll talk about some of these in the context of commercial heifer testing, but the intensity of selection is effectively what proportion of the animals born in this generation get to move on and be parents. So selection intensity is going to be much, much more intense at the seed stock level than it is at the commercial level, both on the side of replacement females, but particularly as we think about which sires get to go on and be a part of that next generation at the top of the breeding pyramid. Genetic variation, of course, is important. If there's no variation in a trait, we can't make genetic progress on it. And then this idea of generation interval. So if we can reduce the generation interval, because it's on the opposite side of this equation, that actually helps us accelerate our genetic gain. So I know that's a lot, but keep this in mind, right? The accuracy of selection, how well does our selection metric represent an animal's actual genetics that they're going to pass down to offspring? And so the way I like to talk about this is in terms of an animal's phenotype being a function of genotype and environment. This slide goes into virtually all of my presentations because it's absolutely essential that we understand these things and how they work alongside each other, not independent of one another. So, of course, the phenotype of an individual has to do with the environment in which it was raised, but it can only pass down this heritable genetic component of a trait. So when we talk about heritabilities, that's the proportion of a trait that's controlled by genetics. So if we think about weaning weight, that's 25% genetic potential, and then 75% of that is going to be how the cow was raised. Did he get vaccinations? Was his dam rotationally grazed? Was there a drought? All those environmental pieces that go into the expression of that genetic potential. So again, we have to dissect these two things out. And in the context of doing genetic selection, we break these out into contemporary groups. So this is pulling out that variation due to the animal's environment. And we focus, of course, our attention just on our statistical estimate of that animal's genetic potential that's an EPD or an expected progeny difference. When we compare these bulls, would we expect their progeny to perform differently in the future? And so this is where genomics comes in. I won't go through and do the full intro EPD talk because I know you've got a good foundation in that. But it's really important that we understand this is only halfway to our ultimate goal of understanding what an animal is actually passing down to its offspring. So we can remove that environmental variation, but we still have to figure out which genetics an animal inherited from its parents. And it turns out there's a fair bit of variation in which chunks of parental DNA an animal gets, right? And anybody who's done embryo transfer and gone out and looked at the EPDs or genomically enhanced EPDs of full sibling flush mates, there can be a huge amount of variation between those. The reason being, and this is a quick little family tree, we'll call these three flush mate bulls. They come from the same sire, the same dam. They share 50% of their sire's DNA, so the combination of the red and yellow DNA, and 50% of their DNA from their dam. But as you can see, when you trace those segments of DNA back to the grandparents' generation, there's some variation in how related this first bull is to his grandparents compared to the second bull. So he's much more related to his paternal granddam and his maternal grandsire than to the other two grandparents. So what this means is that if the red female and the blue male are genetic superstars, this bull got a good sample of those grandparental genomes, and he's probably going to have a higher genetic potential. But we don't, again, know about that when we're just looking at the average EPDs of the parents. So that's where genomics and progeny come into helping us understand which chunks of these parental genomes an animal inherited, and were those the good ones, the average ones, or the bad ones. And so random chance is really the name of the game here. It's what allows us to make genetic progress. If this random chance didn't happen, everything would be exactly as good as the average of its parents. We'd never actually move the needle on from a genetic perspective. So as we think about an animal's genetic potential, it's a function, of course, of half of its sire, half of its dam's genetic potentials. So this is basically saying if you breed two good animals together, on average, you would expect to have a good offspring. But there's also this pesky little thing called Mendelian sampling. I call it dumb luck. But effectively, this is that random shuffle of genes from the parents down to their offspring. And Mendelian sampling variants can account for over 50% of the genetic variation in complex traits. And so to put that in sort of in pounds, right? When we think about weaning weight being 25% heritable, we'll say for ease of math, half of that genetic variation can actually get chalked into this Mendelian sampling term. So we can see a huge amount of variation in full siblings for traits. And again, that's really, really important. We'd like to understand before we invest in an animal, before we invest in semen out of a young bull, if they got a good Mendelian sample or a bad Mendelian sample, or if they're perfectly average between the genetic potentials of their parents. And so the way that this genomic testing works in practice is that we're able to take DNA samples from individual animals in the form of blood, tail hair, have both kind of gone the way of the dodo. Most of what we're doing at this point is taking ear punches with these tissue sampling units. We're able to send these off using those the genotyping arrays or SNP chips, you might have heard them called. We send them off and we observe these places in the genome, these 50,000 or so places that we know are different between animals. And then we turn that into a numerical representation of how related those animals are to their relation or to their relatives, right? We can pull in relationships from cousins, we can pull back those records from grandparents, and as we better understand how related those animals are to each other, we can pull in additional phenotypic information from those related animals that share more of the actual DNA with our focal individual, and that's really the way that we're able to increase the accuracy of EPDs. So again, if we think about my example here, if we've got a bunch of calves that are outperforming their parental expectation, so say the sire and dam's genetic potentials would estimate that calves are going to wean off at 500 pounds, but we start getting a whole bunch of 520-pound calves out of this particular individual, it's likely that that bull got a favorable random sample of those parental genes. That's the sort of animal that we want to select to move on to the next generation, but we don't want to have to wait for all of these calves that he has to get reported back into the evaluation before we know that. And so the way that this works is we see EPD accuracies change in response to genomic tests being used. So these are what we call progeny equivalents. And a progeny equivalent is effectively saying for a given trait, how many records will we need to have out of that bull's offspring to see the same increase in accuracy that we get from a genomic test? And so if we look at a trait like weaning weight, this says that doing a genomic test on a bull is worth 27 progeny records for weaning weight being reported back onto that bull. That's a full calf crop's worth of confidence that we get in increased EPD accuracy through utilizing a genomic test. And it all goes back to this idea that if we can resolve those relationships, if we can understand whether or not that animal got a good Mendelian sample, that dumb luck term, did he get lucky or did he get the bad shake of his parents' genes? This allows us to be much more confident on what that bull's actual genetics he can pass down and into our herd are going to be in the future. And so the bottom line is that genomic tests reduce risk when purchasing unproven bulls or using unproven AI sires. When we think about trying to advance our genetic progress, not only is getting that decision right, so that accuracy of selection important, but the generation interval piece is important too, right? If we're using a bull from 15 years ago, because his accuracy is 0.99, we're losing out likely on, 10, 15 years of genetic progress that has happened in between. So it's preferable, again, from a theoretical standpoint, to use those younger sires. Genomic testing helps us be more confident that those are the right animals and that the EPD that we're looking at, the index that we're looking at, is representative of their actual genetic merit. And so just to sum this up on the bull side before we jump into commercial female testing, genomics works. This is some really nice data from the American Angus Association showing basically pre-genomic selection trends and post-genomic selection trends. So again, in the direction we'd expect to see these traits moving: weaning weight, carcass weight, and ribeye area up, fat and milk down. We see that there's a different rate of change in these two segments of Angus's history, right? So when we add genomics in, it allows us to make genetic progress faster. And one of the most beautiful examples of genomics at work in an industry is from the dairy industry, which anyone who's familiar with dairy breeding knows that pre-genomics, we were sire testing all of these AI sires. So we'd breed to a bunch of test females. They'd go chill out in a barn for 5 or 6 years before we got progeny records back. Those first daughters went into their first lactation, and only then were we able to increase our EPD accuracies in order to make those decisions on which bulls get to stay in AI programs and which ones get to go be hamburger. But what you see here is effectively a perfect inflection point when you look at the sires of both the bulls and dams in American Holstein at basically 7 years old. When we see genomics introduced in 2010, those things rapidly decline. And that leads to not only that decrease in generation interval, but completely different rates of genetic change for a number of traits in the dairy population. And my one last thing I'll say for seed stock producers that are on here is that regardless of whether a genomically enhanced EPD gets better or worse as far as traits or indexes go, it's always better than an unenhanced EPD. And what I mean by that is that the increase in accuracy that we see gets us closer to an animal's true, right? It gets us closer to that true genetic merit that we're actually looking for. What can they pass down to our herd from a genetic standpoint? Even though sometimes that EPD goes up or down when we submit a genomic test on an animal, it's always going to be better because it's closer to biological truth. So with that, no place in the commercial herd that benefits more from genomics than in bull selection. I think that this is absolutely imperative. Again, whether we're using AI, whether we're going out and purchasing herd bulls, making sure that we're doing so with an animal that's got genomically enhanced EPDs is so important. So with that, I'm going to switch gears and spend the rest of my time talking about genomics for commercial heifers. Again, this is a rapidly expanding area, and there's some little intricacies and details and differences between commercial heifer genomic testing and testing on seed stock bulls. And so our traditional heifer selection strategy has typically been buy good bulls, hopefully. Good bulls make good cows. No better way to improve a cow herd than to buy a bull that's got genetic potential for all those maternal traits that we really care about. Use some common sense. And I would really plead with everybody to not stop using common sense. And we'll talk about this in a little bit. And then hope for the best. We didn't have any way previously, aside from knowing the sire's EPDs maybe, or some history on the cow family, of what the actual genetic potential of the heifers that we're investing in and retaining in would be in the future. And so when we think about this phenotypic heifer selection, some of the things that we might think about using as selection criteria, and I'd argue many of these, even in the post-genomics world, are still really, really valuable ways to prioritize which heifers get to stay in the herd. Age, of course, is probably the most used, right? Older heifers are going to start cycling faster. Those early cycling heifers are more likely to get bred their first opportunity. Animals that get bred their first opportunity have a longer anestrus period after that first calf and are more likely to rebreed with that second calf. And we know that that anestrus is so difficult to get animals recycling after their first calf. And you just put an animal, you give them a little boost when you're choosing an animal that's a bit older, right? So there's good reason for using age in your phenotypic heifer selection. We can think about things like pelvic scores, dam performance. We want to keep good heifers out of those good cows that have been good for us. Heifer performance, right? Heavier heifers, heifers that have gotten through that development stage a little bit quicker, might be more likely to get bred with that initial service. And I think one that I think gets overlooked a little bit, but I'm certain plays a big role in a lot of folks' heifer selection is she's got the look, right? I like to look at her. Life's too short to keep back heifers that make you cringe when you look at them. And of course, confirmed pregnant, right? No need to keep those heifers around if they're not going to give you a calf. So as we think about introducing genomics into this equation, we have to sort of draw some lines about what genomics does and doesn't do. All right. And so what genomics does is it does help us estimate genetic merit on traits. It helps us increase the EPD accuracy of unproven animals, or in this case, for commercial heifers, it gives us an EPD to start with. We have a prediction of an animal's genetic potential rather than some of those other more conventional or pure phenotypic measurements. And what these things will inevitably do, no matter what, is they help accelerate population genetic gain. So on average, if we use genomics as our selection criteria, they will help us move that population forward. But what genomics don't do, and I don't want us to get confused about some of these things, is they don't predict phenotypes necessarily for individual animals, or they don't do so perfectly. I've got an example here on the next slide about this, but it's really important, especially for some of these more these female traits that we're interested in, that genomic tests give us some genetic insights for. They're not able to account for the non-heritable, or in the case of crossbred females, non-additive components of traits. So they're not going to give us a pure phenotypic prediction on an animal, but they do give us an idea about what her genetic potential is going to be, that she can pass on down to her offspring. So the example I'll give here is cow longevity, probably the most important female-centric trait that we have to select for. Stayability is the seed stock trait that gets reported most often, but an absolutely enormous chunk of the commercial cow herd's profitability goes into this long-lived cow. If a cow lives past that payback period, we don't have to replace her. She lives longer in that profitable stage of her life. Cow longevity is a very important trait. We all know that. The issue is that the heritability of this trait is quite low. It's 0.1, might be generous. So 10% of this trait is due to genetics. Another 90% is due to that animal's environment, how it was managed as a calf, as a developing heifer, and subsequently as a cow. Lots of things that go into cow longevity. And it's not just fertility, it's feet and legs, it's udder. It's a sort of big all-encompassing trait that's very important, but the heritability of this trait is quite low. So we'll say that 10% of cow longevity is governed by genetics. And our genomic EBV or EPD that we get back in the form of a genomic test, the reliability or accuracy of that is 0.5. So basically what that tells me is that a genomic test score is only going to explain about 5% of the longevity differences in a heifer crop, right? Just the genetic component is all that these tests can tell us. So does that mean that it's not important? I don't think so. I think that still is valuable. But again, it's not guaranteeing anything. If I select that heifer that's in the 99th percentile for a trait like longevity, again, that only explains a small chunk of the differences in that animal's phenotype. So it's really, really important that we continue to use genomics alongside our common sense predictors, age, weight, what's her body condition going into breeding, right? All of those things are important for us to look at alongside these genomics. I don't want genomics to end up being a sort of a silver bullet because it's not one. They're very, very useful tools alongside some of these other common sense predictors. Lots of different genomic tests on the market. And these are going to, the one that you choose will depend on the context of your particular herd. So there are some genetic evaluations, probably the most common would be American Simmental Association, allows commercial animals to be enrolled in their total herd enrollment program. This allows your commercial females to be treated effectively like a seed stock animal within the American Simmental evaluation. So they get EPDs back just like you would if she was a registered Simmental animal. The issue with these, or not issue, there's a high level of additional record keeping that a commercial herd has to do to be a part of this. Our university herds are enrolled in total herd enrollment because those really high level records are getting kept. But again, not for everybody. We also have these genomic tests that don't require any sort of phenotypic reporting back to an entity to get a genomic score. You send off DNA, you get back a genomic scorecard. These will vary a little bit, but probably the two most common that you've heard of would be Igenity product from Neogen or the Inherit Select product from Zoetis. Zoetis also has a GeneMax Advantage product for straight bred Angus commercial females. But these multi-breed commercial tests are the ones that have grown the most in popularity. They'll tend to send back trait reports for, I don't know, probably close to 20 different traits and a handful of different economic selection indexes, which again is how I always encourage folks to think about their selection indexes as being sort of that first line of selecting between bulls because they're able to integrate a number of different traits into one number that's really centered on the genetics that underlie profitability. And so I won't go too far into the weeds here, but there's basically two ways that you can approach genomic testing for commercial producers. The first is to just throw an animal into a genetic evaluation like they're a true member of the genetic evaluation. Very similar to how we would fit these animals if they were purebred animals in one of our purebred seed stock evaluations. We can also use the marker effects. So basically, looking at all 50,000 of those DNA markers and asking how much does each version of that marker contribute to a phenotype that we're interested in, adding those up across the genome, and then reporting back a single number that reflects that animal's genetic potential. So some differences here. The important piece is that in particular for the marker effects model, the animal's population that it comes from and the population in which that model was trained in, they have to be related to one another. Otherwise, these predictions aren't necessarily portable from population to population. So again, we've got reference population who has both markers and phenotypes measured. We train some sort of a model that uses those effects of the markers times the marker genotypes themselves, gives us a prediction. And then we use that prediction to predict into these animals who don't have phenotypes reported, but do have genotypes. We make our selection based on that, what they call a molecular breeding value. The issue, of course, right, is if these two populations, the population you train the model in to get these effects, is very, very different from the population that you're trying to predict in, the accuracy of these things goes down the drain, right? I wouldn't want to use one of these models that's trained in an American Angus female population to try and predict into my Hereford population. It just doesn't work, right? So we've got to be sure that there's representation in this training population of the animals that we're trying to predict into. The long story short of it all, though, is that commercial genomics does work on average. This is some work that I was a part of during my PhD at the University of Missouri. This was evaluating that GeneMax advantage. So that was the commercial straight bred Angus test on a big population of research center cows. And basically, what we did here was we said we've got a score on the dams GeneMax, we've got a calf performance. How predictive of the dam's GeneMax score, or how predictive of the calf's performance is the dam's GeneMax score? And you can see these are kind of big blobs of points, but there's a trend in these lines, right? As GeneMax score of the dam goes up, all of these calf phenotypes also tend to go up. Is the dam's GeneMax score perfectly predictive of all of her calf's performance? No, it's not, right? There's a fair bit of noise around each of these regression lines, but on average, there is still a linear relationship between the dam score on that genomic test and how her offspring perform. And this is why I say it's really important that we not think about these as phenotypic predictions on individual animals, but rather we think about them as a tool that's going to help us move the needle on the population faster, right? They help us get the decision right more often than if we were just flipping a coin. The issue or not an issue, but one of the things, again, to keep in mind about genomic tests is that seed stock animals are the major driver of genetic trends in the commercial cow-calf sector. I've run some simulations, and basically what we've got here are three populations. The red population is a commercial herd that's genomically tested. The green population is a commercial herd with random selection, so we're choosing our replacement females at random, and then the blue is our seed stock herd. And so what we see here is that the slope or the rate of genetic gain across these 5 generations of selection, the rate is actually determined by the seed stock individuals that we're pulling in, right? These lines all run in parallel. We get a little bit of a boost here in the first generation of selection of those replacement females, but really the big driver of genetic change over time is coming from this seed stock population. And so if we think about genomically testing heifers, it's really, really important that if we're going to use this information to make decisions, we've got to test more heifers than we're planning to keep. So if we're only testing heifers that we've already decided we're going to keep, we've basically just thrown $30, $35 down the drain, right? This has to be used to make actionable decisions. We need to test probably our top 2/3 of heifers and use that to make decisions. So again, testing more heifers than we plan to keep is imperative. Otherwise, this is, as I say, really expensive confirmation bias. So I've talked and maybe tempered a little bit of expectations about commercial genomic tests, but I want to talk about 3 other areas outside of making commercial replacement heifer decisions that I think are really, really valuable, maybe even more valuable in reasons that the right commercial herd should consider using genomic tests. The first, I think, is probably to identify animals with the highest heterosis potential. Understanding that these replacement female traits, fertility, health are all lowly heritable, we also know that heterosis plays an outsized role in these. Cow longevity, for example, 0.1 heritability, but the heterosis that we expect in a crossbred female is something like 25%. So again, I would really like to use these genomic tests to identify which heifers are the most heterozygous, right? They have the most potential for expressing heterosis in those replacement female traits we're so interested in. Genomic tests can allow us to do this. I know that both Zoetis and Neogen report some form of prediction of an animal's heterosis potential or hybrid vigor potential, and that's a really, really great way if we're going to look at those females, not just the additive part that comes out in those predictions in the form of genomically enhanced DPDs that we get back, but really looking at their potential to express hybrid vigor. That's a big area that these tests have can play in our herds. The other thing is they can help us make more precise mating decisions, help us choose the right bull. I've just gotten done telling you that getting your bull decision right is so important. But if we understand both at the whole of our heifer crop, but even on an individual heifer level, if we're using artificial insemination, we can start to make strategic mating decisions between these animals when we understand what a heifer crop or an individual animal's strong and weak points are. That allows us to go out and pick a bull that can complement those weaknesses, bring his own set of strengths, and add value to that animal, and help us move the needle faster. Again, understanding that these bull buying decisions, AI sire selections, are ultimately going to be our big picture drivers of genetic progress in commercial herds. And then finally, I think there's a lot of programs that are about to emerge that will allow us to use genomics to add value to our feeder calves, sell our feeder calves based on the potential that they have genetically before they've gotten an opportunity to express it, especially as we think about that post-weaning gain, carcass merit. People that buy cattle, whether they're feed yards or otherwise, are interested in having more information, and programs are emerging that allow us to capture some of that value from the genomic tests. I've written um, a sort of white paper, our eBeef group. It's a big group of genetic extension specialists. I wrote one of these fact sheets a couple years ago about value-added programs that are tied to genetics. So genomics and sire verification, I think very useful tools to helping market feeder calves. So I'd encourage you to have a look there for some more in-depth information. I want to skip through some of this and answer some questions. I don't know if there's any in the chat, but other than talking about all of the complex sort of return on investment that we need to do, just a couple of takeaways there. My contact information and happy to answer any questions if we've got them.
Great. Thank you, Troy. I'm gonna basically go through the Q&A box here and read some questions out loud for you. And yeah, let's approach it that way. So for those of you that are they're connected and you want to ask a question, if you look at the bottom of your screen, you should be able to see a Q&A box. If you click on that Q&A box, you can type your questions there. And we're going to be, like I said, reading those questions out loud, and Dr. Rowan is going to be answering the question. So the first question that we have here, Troy, is how soon can you do a genomic test?
Yeah, that's a really good question. And the best thing about genomics is that that doesn't change from the moment that fertilization happens, right? That animal's genome is going to stay the same from fertilization through the end of its life. So there are some cases where people are actually they're making IVF embryos and they're going in and doing genomic tests on the IVF embryos before they decide which ones they want to transfer. Only the very, very best embryos based on genomic scores get transferred. The others get tossed or put in, dairy cows or something, right? So I think that that's happening at the high level of purebred operations. Functionally, though, as a commercial producer, you can, whenever it's convenient, you can collect that genomic sample. So if that's it at pre-vaccination, the really or pre-weaning vaccination, the important part is that you've got to give yourself enough time to get the results of that genomic test back in order to make a decision. So if you go out and collect DNA samples the week before you're going to ship your cull heifers, that's probably not going to be enough lead time to get those insights back and use it to make a decision on which females get kept back. So again, you can do it the sooner the better. Collect those DNA samples when it's convenient, but make sure you give yourself enough lead time such that you can use that information in a decision.
Great. The next question that I have here is it's more of a request for you to comment on the Leachman index for inherit select in
Yep.
comparison to indexes with the base test. Do you find value in them as an add-on?
Yeah, that's a good question. I'll add maybe just a little context. The Leachman indexes are optional add-ons to the Zoetis Inherit Select product. The Leachman genetic evaluation is really um, a big multi-breed evaluation that powers those genomic tests. So those animals effectively that are Zoetis tested get fit in that big genetic evaluation with all the Leachman animals. There's the option to add on Leachman's dollar profit and dollar ranch indexes. I think that those are nice indexes. The Leachman folks have worked on them for a long time. I also have seen the Zoetis indexes, and I think that again, depending on your marketing endpoint, their total return index or their cow calf index that Zoetis reports back, I would expect those to be quite highly correlated to the Leachman indexes. But it really just comes down to personal preference. If you have a way to market calves with one index or the other, that certainly could be enough of a return on investment to see that. So again, that's a non-answer, but I think they're both good indexes. There might be some value, but sort of do some digging on those indexes and see how their assumptions match up with how you market your animals or how your heifer retainment selection process works.
All right, so the next one that I have here is will I be able to sort full brother ET bulls for economic traits with multi-breed testing?
Full brother ET bulls with genomic tests, or full brother ET bulls with commercial genomic tests. Is that more or less the
That's
question?
that's more or less what I understood. So basically, will I be able to sort full brother ET bulls for economic traits with the multi-breed testing?
Yeah, so the multi-breed tests will work on. I would assume these are probably purebred bulls.
Mhm.
Um, I would say my rule of thumb is that you're always, if you've got a purebred registered animal, you're always better off having that animal evaluated in a full genetic evaluation rather than getting a multi-breed commercial genomic test back on them. There's so much more data powering those. The relationships between animals are so much tighter. That's going to give you a more precise, more accurate breeding value than getting a commercial genomic test on that animal. But again, regardless of whether you do that or a commercial test, you should see a fair bit of variation between those full sib brothers. Again, just due to that Mendelian sampling, there can be some wildly different EPDs between those two, just due to the random sampling of parent genomes.
All right, so the next one that I have here is I'm not clear on how would ID animals with high heterosis potential. Are you saying that within breeds, some genetic combinations have higher levels of heterosis?
Yeah, that's a great question that I should give some more context on. Um, uh, Without getting too far into the weeds, one indicator for the amount of heterosis or hybrid vigor that an animal will express across traits is the amount of heterozygosity. Again, that's effectively a measure of genetic diversity across their genome. How many of those sites have opposite alleles or have the opposite version of an allele at each position? So the more heterozygosity that we see across the genome, the more we would expect to see hybrid vigor out of that animal across traits. It's an indicator, and heterosis is a really tough nut to crack. One of the things my research program is really interested in. But again, we found that, and there's a number of papers that have been published that genome wide or across all of the markers on a genomic test, looking to see the proportion of heterozygous sites, or these tests will also do breed proportions. So they'll estimate which ancestry certain chunks of DNA came from. And there's also, it's called residual heterozygosity that's based on that breed proportion. So there's some mathematical ways that they can estimate the degree of heterosis that you would expect out of those animals, but it's more or less based on the percentage of heterozygous to the percentage of homozygous sites as you look across all the markers.
The next question that I have is if you wean 100 calves and you intend to keep 30 replacements, what's the minimum we should genomically test?
Yeah, it can make me do math at 9 o'clock. But so I think that if you're trying to keep back 30 heifers, my rule of thumb, and out of 100 total calves, or that's 100 heifers.
100 heifers. Yeah,
100
100
heifers.
heifers. So out
Yeah,
of
yeah.
100 heifer calves,
My rule of thumb is test twice as many as you plan to keep. So if you're going to keep 30, test 60. The important thing you've got to keep on in mind as you're doing return on investment with these things is that the test cost has to get spread across those only the heifers that you keep, right? So if a test costs you $25, each replacement heifer that you keep is going to have to bear $50 worth of testing costs. And I think just a quick aside here as I'm reminded as I'm talking about return on investment, the one thing, and I think I maybe skipped over this in one of my last slides, for commercial operations that aren't spending sort of the max, if they're not buying the best bull that they can get, I would always argue that reinvesting the cost of commercial testing in the best bull that you can get within reason, I think is always best, right? But there's a lot of us that are spending money on the best bull or the best semen that we can buy. And that's where I think genomics and in doing this math to see if you can generate enough additional revenue, save enough on those replacement females to cover that testing cost across the heifer and the tested individuals that don't get to stay on as replacements. So that was a long, circuitous answer, but a good question.
so the next one is can genomic testing in commercial cattle verify parentage?
Yeah, a great question, and one of the things that I think that both commercial testing companies are very interested in is using it in that sense. And so the one caveat, of course, being that in order for parent verification to happen, that animal's parents also have to be a part of that evaluation. Zoetis, I believe, I'm more familiar, has a test that you can do on your herd bulls per se to allow them to go in and be parent verified as you send those replacement females information in that allows them to sort of be linked. Very useful, of course, if you're testing heifers from multi-bull breeding pastures and understanding how those bulls are going out and working too. Another useful part of these commercial genomic tests.
And do you have to test the bull as well to get that parentage information?
Yeah, Bull's genomics have to be integrated into that system in order to do that parent verification.
Okay, what is the best way to choose genomic test for commercial cattle that uses a three-way cross and or Senegal cattle that aren't one of the usual breeds makeup? Um, we also breed Senegal bulls. How do we find the best test that will have the closest makeup to our herd or breed? So basically, three-way cross was it looks like with some Senegal influence there. Yeah,
Yeah,
how would you recommend they use genomic tests in that settings
yeah,
in that bed?
that's a really good question, and I'll admit I'm not 100% sure what representation from a breed standpoint looks like in both of those populations, the Zoetis and Neogen tests. So I'd encourage you to reach out to representatives from either of those folks, and they could help you figure out if that commercial test is going to have enough predictive ability in your three-way cross or if there's, I think that Brahmin typically is represented in those training populations to a degree. But again, the specifics of Sinopol, not certain if either of those have large or adequate representation of that breed. So would be worth checking into that with each of those testing companies to figure out which one would be the better fit for you.
So the next question kind of build up on that. So if the population that you're sampling is very different than the reference population, can you use the commercial genomic test to at least compare individuals within the same herd, assuming that that herd is quite different than the population that generated the test?
Yeah, that's a really great question, and without doing a bunch of testing, my inclination is to say that again, it's all about your level of risk that you're willing to accept. We would expect that the less related you are to the testing population, that relationship between genomic score and actual genetics is going to get more and more divorced from one another. So I would expect that the further away you get from that training population, the less predictive, even within a herd of related individuals, I would expect those genomic scores to be. So I would tread with caution on that front, just understanding that it just gets noisier and noisier, and being able to tease out the even within a related population is going to get a little bit more cloudy.
So the next question is, can a breeder obtain the amount of heterosis in an individual from the ASA or CHR genomic test?
I don't believe that those, assuming that that's like an ASA, like an American Simmental Association genomic test, they wouldn't report back indicators of heterosis in those. Simply will return back those genomically enhanced TPDs.
So the next question is, how do you recommend the heterosis tests for selecting heifers? What is the value between the same question we have? What is the value difference between an F1 heifer versus a straight bred, assuming the additive gene effect is the same? So in other words, let me try to rephrase this. So how do you recommend using the heterosis from these tests for selecting replacement heifers?
Right.
And do you see value in F1 heifers versus straight bred? I think I
Yep, yep. No, I think I've got that. So I guess the first half of that question, how do you value the heterosis? That's a tricky one to put a dollar value on, right? It's I would use it alongside an index, right? Understanding that the index captures that animal's additive genetics, but also that heterosis is going to be more predictive of that individual's lifetime performance and lifetime productivity. So I would sort of use them in concert. Don't use one completely absent to the other, but try and analyze those alongside each other. If you've got borderline heifers based on the index sort, looking at the heterosis scores of those would also be quite useful. Or maybe a heifer drops down into the bottom third, but she's got a ton of heterosis potential that we'd expect to show up across those reproductive traits. She might deserve a more careful look from a replacement standpoint. And then the question about F1 versus straight bred females, again, it depends on the cross that you're making. We get more heterosis the more diverged breeds we cross. So a Brahman Angus is going to have a lot more heterosis than or an F1 Brahman Angus will have more heterosis than an F1 Red Angus Black Angus. But again, lots of work done at the Meat Animal Research Center that would say that F1 female over the course of her life, on average, is going to have an extra calf. So in addition to all the heterosis that we see in weaning weight and milk production, so that maternal component of heterosis, just the cow longevity that we get from added fertility and health in that cow is going to be worth about an extra calf weaned over the course of her lifetime. So those F1 replacement females are incredibly, incredibly valuable in my eyes. and crossbreeding remains one of our most underutilized tools in the industry. So, good questions about my favorite topic to speak on.
Great. And so the next question is, in commercial tests, is it possible to know the reliability of each trait? Uh, Maybe something similar to an accuracy in a traditional EPD.
It's a good question, and I'm sorry that I can't answer this off the top of my head, but I'm fairly certain that neither commercial genomic company reports an accuracy or reliability along with their EPDs. If someone from Zoetis or Neogen is on and wants to correct me, feel free. But I'm fairly certain that accuracy or reliability aren't reported on those reports that go back on those EPDs. But I very well could be wrong.
The other question is, does the commercial test offer sire selection according to genomic matching?
I don't believe that it does any explicit genomic matching, like a right mate sort of product. I do know that at least Zoetis and maybe Neogen will sort of they send a report card back, sort of a summary that goes through and analyzes the full herd's genetic makeup and points out some areas where bull selection might be better focused on, right? It might say, hey, you're running a little bit low on milk. That might be a trait that you focus on. So it's less precise as far as making genomic matings to try and match large effect alleles, but does give you some prescriptive ideas about areas that you might focus on from a breeding and sire selection standpoint.
Okay, so the next question actually comes from Costa Rica. So we got a question here saying we do not have anyone, to my knowledge, in Costa Rica doing genomic testing.
Hmm.
What partnership or resources are needed to develop a genomic database specific to the Costa Rican cattle populations?
Yeah, and I will claim ignorance on the makeup of the Costa Rican cow herd, but I would think that again, depending on the breed makeup of that cow herd, understanding a little bit more about that would help us point towards partnerships or areas to start that. I know that some places do sort of genetic evaluation as a service, but if there's the ability to plug into one of these commercial testing platforms, provided that your cow herd is represented in some way, shape, or form. That might prevent a reinventing of the wheel, but again, very dependent on the breed makeup of those cattle.
All right, so I'm going through and I'm scrolling down in the Q&A box, and I think I'm gonna get ready to wrap up. There's still a lot of questions, which I think it's a great thing. It means folks are engaged with the presentation and they have questions to ask. So, but I don't want to hold Dr. Rowan here for too long as well. So we're going to get ready to wrap things up here. So as you can see in the screen, that's Dr. Rowan's email information if you want to send him a question directly. And also keep in mind that the Beef Reproduction Task Force, so beefrepro.org, has an Ask the Expert tab there that you can click to send us questions. So with that, Troy, I want to thank you again for the presentation. We appreciate you taking the time. I think this is an outstanding topic, a very relevant topic. I get questions all the time about commercial testing, mostly in replacement heifers, and you did an outstanding job covering that for us today. So with that, I want to thank again everybody for joining us today, and stay tuned in our social media. We're going to be announcing our next webinar soon. So again, thank you very much for attending the webinar.